This video is part of an online course of multivariable calculus, and I'm gonna set up a triple integral to calculate the volume between two paraboloids. So let me start. I want to calculate the volume of the solid that is between these two paraboloids. Let me graph them first. So I have x-axis, y-axis, and z-axis. So z equals to x squared plus y squared. I'm gonna set 0 for z, so I get the origin. And then z, when z is equal to 1, I get a circle of radius 1. If z equals to 2, I get a circle of radius root 2. So I get this paraboloid in here, which is z equals to x squared plus y squared. And how about this one? When z is equal to 0, I get a circle of radius 4. And then when x and y is 0, I get at the point 4. So let me assume that this is the point 4. And then I have like this paraboloid in here. It's circle of radius 2 in the origin. So this one is z equals to 4 minus x squared minus y squared. Okay, so the region that I want to calculate this volume is this region in between. Actually, let me show it to you, the shape. Using a program, maybe it would be easier to understand. So this is z equals to x squared plus y squared. X-axis, y-axis, and then z-axis on top. And then I have this paraboloid in here, 4 minus x squared minus y squared is here. So the region between these two would be this region that is on top, bounded by 4 minus x squared minus y squared, the green one. So let me make the other one hollow. Okay, maybe I should make this one also hollow. So you see that it is like, let me change this one a little bit, that one a little bit. Yeah, you see it's like kind of like an egg, if I'm correct. This is the volume of an egg that is between these two and here that I'm calculating. I hope it makes more sense. Yeah, you see, this is on the bottom, it's bounded by this paraboloid, and on top by the other paraboloid. Okay, so I want to calculate the volume, but before that, let me give you a recall. If you remember, the double integral of a function f of two variables, dA over r, it calculates the volume for me, which was the volume of what? Oops. The volume of a solid that is bounded by on top by the function f, on the bottom by the region r in the xy plane. So this is the region in xy plane. And when I want to calculate the volume of the solid in here that is bounded on top by f, on the bottom by r, I use the double integral of f. Okay, and then the double integral, if I put 1 in there instead of the function f, then you see that the height of the solid would be just 1. So this volume becomes 1 times area of the base. So that's why if I put 1 in there, I get the area of the base r. Okay, so now that I want to calculate the volume in here, I can use the double integral, but the region should be in the xy plane so that I can use the double integral. That's why I use the triple integral to calculate the volume, because the bottom boundary, it's not on the xy plane. So the volume of the region, let me call it R in here, is the double integral. Let me call this one R, or maybe let me call it S to emphasize that it's a solid. Of S is the triple integral of 1 dv over S. Okay, so one more time, I cannot use the double integral. It's just because the boundary on the bottom is not on the xy plane, it's right there. Okay, that's why I use the triple integral for that. Okay, so now let me calculate the boundaries. Okay, so the first step, I want to say that for a fixed point x and y, what is the range of z? The range of z from bottom, it would be from here. So let me graph a parallel line to the x-axis, to the z-axis. This is the point on the boundary on the bottom, which lies on this cone. Z equals x squared plus y squared. It's the bottom face, and also on top, it's bounded by the orange cone, which is z equals to 4 minus x squared minus y squared. This is the top face. Okay, so when I set up the triple integral, z is from here to the top. So z is from x squared plus y squared to top, which is 4 minus x squared minus y squared. Okay, now I need to see what are the values of x and y. Okay, so this is the second step. What values of x and y we should consider? So to find the boundaries for x and y, I need to find the shadow of the region S into xy plane. So I need to find the shadow of S into xy plane. Okay, look at the solid. You see, x-axis, y-axis, and then the z-axis. The solid is something like this. It is like that. Okay, and then this is the solid, and as you see, the boundary, if I want to consider the shadow of this one into the xy plane, I need to basically look at the intersection of these two cones. Okay, the intersection is the circle. This is like the boundary of the shape that I get the shadow of, yeah, into the xy plane. Okay, so I say the boundary of the region D in xy plane is the intersection of these two paraboloids, which is what? I'm gonna set x squared plus y squared equals to 4 minus x squared minus y squared. I'm gonna bring these two on the other side, so I get 2x squared plus 2y squared equals to 4. So it would be x squared plus y squared equals to 2. So now I can say that x, y, and the intersection would be a circle of radius root 2. This is root 2. That's the circle. Okay? And this is the region. Now, when I want to set up the boundaries for that, let me do dy first. When I want to do dy first, I graph a parallel line to the y-axis, the beginning point, the end point. This point lies on the curve negative 2 minus x squared, and this point lies on the top half of the circle. Actually, I wrote this wrong. And this is y equals to negative 2 minus y squared. Oh, actually, positive 2 minus x squared. Okay, very good. So now let me kind of set up everything together. Okay, what do I have? The triple integral of 1 dv over the region S would be dz. Z is from x squared plus y squared to 4 minus x squared minus y squared. And then I have dy. Y is from here, which is negative 2 minus x squared to 2 minus x squared. And then dx. dx is from here, which is negative root 2 to here, root 2. Okay? That is the integral. Let me solve the inner integral. The inner integral is the integral of 1 dz, so it would be z from x squared plus y squared to 4 minus x squared minus y squared. So it would be 4 minus 2x squared minus 2y squared. Okay, so I have negative root 2 to root 2, negative 2 minus x squared to positive square root of 2 minus x squared, and then I have 4 minus 2x squared minus 2y squared, and then dy dx. It's a little complicated to solve this integral, and this is just a double integral in x and y. And notice that the region of integration for this double integral is a circle. That's why when we have something complicated in x, y, and the region is part of a circle, we're gonna switch it into polar. Okay, so I'm gonna switch into polar. Okay, when I switch into polar, what do I have? I have x as r cosine theta, y as r sine theta. So I have what? I have the double integral. I'm gonna write everything in polar. I have dz, and z is from x squared plus y squared. In polar, it would be r squared. This one in polar would be 4 minus r squared. And then dy dx in polar would be r dr d theta, or where the shadow of the region in xy plane is this thick, and in polar r is from 0 to the radius root 2, and then theta is from 0 to 2 pi. Okay, now you see that this integral is very easy to calculate. So I'm gonna start with the inner integral. This one, the integral of 1 dz would be z, and z is from r squared to 4 minus r squared, which is 4 minus 2r squared. So I have the integral from 0 to 2 pi, 0 to root 2, and then I get 4 minus 2r squared. I have r dr d theta, so I'm gonna multiply r in here, dr d theta. Okay, so I get from 0 to 2 pi, and then it would be 2r squared minus 2 to the over 4 r to the fourth. R is from 0 to root 2 d theta. And let me plug in root 2. So I get a 2 in here. Together would be 4 minus 2 over 4. This one is also 4, which will be cancelled out with that. So I get a 4 minus 2 d theta. So it would be 2 times theta from 0 to 2 pi, which would be 4 pi. Okay, so this is the volume of the solid that was in between two paraboloids. And you see at the end, this integral was kind of hard to calculate. That's why I switched it from polar, because the region of my integration in the xy plane was a disk, and this is basically the cylindrical coordinate.